Hello, everyone. So today I'm going to talk about linear programming. So somebody already asked me a question, is this about pipelines? No, and that's exactly why I want to talk about it, because I think it's a topic which is criminally underrated, and I want to sort of like maybe put it on your radar. So the plan, first, I'm going to talk a bit about why is it that I even want to talk about linear programming, because maybe if you didn't hear about it, maybe there's a good reason for it. Then I'm going to introduce linear programming. In 30 minutes, I can't do a full topic deep dive into it, but I want to give you a sense for what is it and how it works. And then I'm going to go into the fun parts, which is beyond linear programming. There is a piece called mixed integer linear programming, which is where you can go from I can do useful stuff to I can do really interesting stuff. And finally, I'm going to talk a bit about applications, limitations. And as mentioned before, tomorrow there is a workshop where if you want to know more about this, there is going to be 3 hours, knock yourself out on doing a linear programming. That's right, that's the spirit. So let's get into it. Quickly, my name is Mathias Brandewinder. I realized, I don't know if it's good or bad, but I started F# initially completely by accident. Somebody told me you should learn new languages, it's going to be good for you, and so I just gave it a shot. And I thought I would just try it for a few months, and it's I realize now that it's actually 10 years since my first blog post about F#, which is kind of crazy. So it's 10 years of F#. But before I was doing C#, F#, all these things, my real background is in economics and operations research. So if operations research roughly revolves around optimization, give me a function, I'm going to find you the best possible, the optimal values for anything. That's my background. And this is relevant here because maybe if you've heard about me, it might be because of the combination of F# and machine learning. I've done a lot of that over the past years. And as a result, people come to me and to solve in F# machine learning projects. And I've heard a sentence a lot. We need to solve this problem with ML or AI. And in lots of cases, it's sometimes it's true. Most of the times, it's do you really? That problem looks like you absolutely don't need machine learning. And there are many things you could use for that. And one of them is linear programming. And so I'm going to sort of diss at machine learning during this talk, which is a weird thing for me to do because I'm the machine learning guy. But I want to put on your radar that there is other things you can use LP and MILP. The other reason I wanted to talk about it was linear programming is great, but you sort of need a solver or a library to use it. And for the longest time, all you had was pretty expensive libraries, which were great, but unaffordable for the casual developer. Turns out, since I think 2 or 3 years, Google has actually released a really nice library called OR Tools, which is a pretty solid LP, MILP library, so you can actually do something pretty serious with it for free. So that's 2 reasons to care. So let's go into linear programming. It's not a cutting-edge, bleeding-edge topic. The algorithm dates back to the 40s. You might be aware that in the 40s, a lot of things were happening in the world, and people needed to move lots of people, lots of stuff around. And so the problem of efficiently allocating resources to people, to places, was a big problem. And so that's where linear programming started. Actually, it started both on the Russian side and the American side for similar reasons. Maybe one of them was the plan and the other one was the war. But the core algorithm behind linear programming is called the simplex algorithm. Was established, I think, mid-40s by a guy called Danzig. And there is a bunch of very big names involved in the development of the algorithm and what happened before. But point is it's an old algorithm. What does the algorithm do? It's going to solve something if you give it a linear objective function and you give it a set of linear constraints, it will give you the optimal values for the variables. Technically, I could stop the talk here. This is what linear programming is. Now, if I tell you this, your reaction might be this is great, this is entirely useless, what does this even mean? So what I'm going to do next is going to go through linear programming through a small example, not going to develop it in great detail, but I want to give you an intuition for what the algorithm does and why it might even work. So let's do that. I heard that burritos were like the perfect topic to explain many things, including monads. I figured why not use it to explain linear programming. And so coming from California is like, I'm going to look at the example of like, I want to build the perfect burrito. So I'm going to build a burrito. Unfortunately, the only thing I have available is avocados and baked beans. The avocados is great because it starts with an A, baked beans with a B, which is going to help me with notation. And my goal will be like, I'm going to build a burrito for myself, and I want to satisfy my dietary requirements. Like I want to have enough calories, I want to have enough vitamins and all these things. That's kind of what I want to do. All I have for that is avocados and baked beans and a burrito. So let's build that burrito. Whoops. Sorry for that. The first, so this is actually real data, like I had to check for like requirements. One of the requirements, like every day you need to ingest enough potassium, otherwise if you don't do it for long enough, it's like bad things will happen. So we absolutely want to supply enough potassium. So if you look on the internet, the source of all truth, you're going to see that an avocado, a serving of avocado, which is like a half avocado, will give you about 10% of what you need every day for potassium. And if you take baked beans, a serving is like 1 cup. 1 cup of baked beans is going to give you 19% of daily needs. What we want is a burrito which is going to give you 100% of what you need. That's what you want. So how does this translate? Well, one way to write this would be to the equation below, which is like if I take an avocado, any unit of A is going to give me like 10% of what I need every day. For instance, like if I had like 10 avocados, I would be done. Baked beans, 19% per baked bean. And what I want is like a combination of avocados and baked beans, and I want to have more than 100% of what I need every day. So this is how the requirement of potassium translates. 0.1 times A plus 0.19 times B greater than 1. Good. So if you do a bit of fiddling and moving data around, you could rewrite this way. 0.19 times B greater than 1 minus 0.1 times A, which is going to end up as B equals 526 minus 0.52 times A. Why did I do that? Because like if you squint a bit and remember maybe your high school classes, like this describes like a straight line. This is like a linear equation. And so I could actually plot it on a graph like this. And what I'm plotting here is like my x-axis is avocado, y-axis is baked beans. And so the equation I had right before, if I plot it here, is like this is the line here. Anything which is under that line means like I'm not getting enough potassium with that particular combination. For instance, if I take like 0 avocados and 2 baked beans, I'm not hitting the level I need. If I go at like 5.5, I'm good. And so everything under is out, and everything above is what's called the feasible area. Like if I take any combination here, is a combination where I'm going to get enough potassium, and so I'm good to go. Great. Progress, like our magical burrito is in progress. And so now if you keep looking at this, you're going to see that you don't need only potassium, you will probably need calories, you will need vitamin C, vitamin A, like whatever. You might also want to do things like, I don't want a burrito which is more than 17 kilograms. Maybe I don't want a burrito which is bigger than a cubic meter, all these things. And actually, if you start to look at this, the point here is like if I take vitamin C, I'm going to get something quite similar. It's like a serving of avocado is 11% of daily needs, blah, blah, blah. I'm ending up with an equation which is pretty much the same as the one I had here with different values. If I did the same for the weight, I would end up with also structurally the same type of equation, and so on and so forth. So the point here is that there is a pattern which is emerging. It's like if I look at all the requirements I have, all of them will end up looking like variable A, avocados, multiplied by A constant, which I'm going to call the coefficient for A, and variable B, baked beans, with A coefficient less than a constant. This is what's called a linear equation, because like it translates to a straight line. It's also called like a linear combination, and like all of what it is like it's a sum where like the only thing I'm allowed to do is like take a variable, multiply it by a number, and like sum them together. That's a linear equation. And if I do that, is like, you can see that this is going to define a straight line, or more generally, a half plane. So now, so this is interesting because now it's like if I have not one equation, but like 2, 3, 4, 5 requirements, I can still put them on the same graph. And what am I going to get here? Is I'm going to get a lot, I have a first constraint here, which is going to define this is not allowed, this is feasible. Another one, which is going to define like a place you can do, cannot do, and so on and so forth. And if you put all of them together, you're going to end up with a polygon, like a convex polygon, which is the feasible region, a feasible area. If I put all the constraints together, this is telling me like these are the only burritos you can do if you want to meet all the requirements. Progress. And like if you add more requirements, it's going to be more of the same. Now, I'm a capitalist. I live in the United States. So it's like I want a burrito which gives me the requirements. Obviously, I want the cheapest possible burrito. Like I don't want to waste money here. And so I'm going to look at what would be the cost of my burrito. I can look up the price of avocados. Maybe it's like 50 cents per avocado, 25 cents per bean. And so if I wanted a burrito which cost me $1, I would end up with an equation which is 1 equals 0.5 times A plus 0.25 times B. That equation should be familiar because it looks incredibly similar to the equation we've seen before. This is another linear equation. So what I want is like the objective, or like what I want to maximize or like minimize, because it's the cost here, is a straight line. So I can plot it on my chart again. So I have my feasible region. In here are all the burritos I can actually use. And here is the line which is showing me, like, if you want to do a $1 burrito, it has to be on this line. There is clearly a problem here, which is like, this is what I can do. If I want $1, there is no burrito I can produce for $1. So that's problematic, but like I'm a resourceful capitalist, is like I'm going to change the price. And so, or in other words, what I can do is like what I want is like I want to move that line as little as possible so that I get a burrito which is feasible and so that it's still as cheap as possible. And so if I do that, I'm going to move this line here. And like by moving the line, I'm going to hit the polygon at some point, which is going to give me the cheapest possible feasible burrito of all the burritos I could do. Great, so we have an optimal burrito. What I walk you through here is the simplest possible linear programming problem you could solve with like 2 variables. And this is more or less what the algorithm I described before, like the simplex does. It does it a bit differently, but behind the scenes, this is what it does. It looks at all the constraints, creates the polygon, and you give it like a linear objective, like the cost here, and it's going to move it until it hits the polygon on one of the edges, and that's the optimal solution. So if you could only solve things for like 2 variables, that would be a bit limited. Like who needs an algorithm to solve for like beans and avocados? But like with a bit of hand waving, I will ask you to trust me. But like if you had like 3, 4, 2,000, 2 million ingredients, the algorithm would look exactly the same. The difference would be where we had coefficient A times A plus coefficient B times B, we would end up with like n variables, like x1, x2, xn. The objective function would be c1 times x1 plus c2 times x2, and so on and so forth. So it's just the same thing with just way more variables. The constraints will look exactly the same. These are still linear. And like if you have this structure, the simplex algorithm will work exactly the same way. It creates in 3, 4, n dimensions a polygon. It will create a plane. So everything works the same. This is just where like you need to believe me, but like it's more is the same. Cool. So this is what linear programming is. If you want to solve a linear programming problem, you need 3 things. You need to define the variables you care about, like in our case, like the ingredients or how much of the ingredients. You need to tell it what is it that you want to optimize for, like what is it that you want to maximize, and that function needs to be linear. That's the only constraint, and you need to give it a bunch of constraints which need to be linear. If that is the case, you are done. You give it, you press solve, and you will get an optimal solution to the problem. It's a very powerful algorithm. Essentially, like if the problem is linear, it's solved. And it gives you, like, I'm going back to the topic of like machine learning. Compared to machine learning, it gives you like extremely powerful results. Like the first one is like if you have a linear programming problem, you will know for sure that the solution you get is optimal. This is not the case if you use gradient descent, all these techniques where like you hope that you get maybe a local optimum and you kind of guess that you're close to the real optimum. Linear programming is like, it is the best you could possibly get. The second one, which is cool, is like it handles constraints directly. Gradient descent is great. If you have something like, I want to minimize a function, but I also want certain variables to be greater than 2, satisfy some constraints, you're entering a world of pain. It's really hard. The linear programming, like, eats that for breakfast. This is what it does. You can give it constraints. It will give you the best solution under the constraints. The other one is like it's surprisingly fast. It's actually a research topic. Is like, you know, big O notation. And is like there is, as far as I know, there's still research on like how low is n actually. Like in practice, the simplex and the algorithm works kind of better than what people would expect typically. Like it's a pretty efficient algorithm, and it's suitable for large-scale problems. And so when I say large-scale, I give you like the case of like 2 ingredients. A problem with like 1 million variables is not uncommon. Like it's been built for like large-scale planning. Like think Marshall Plan, think like Russian Plan. Like thousands of variables, like doesn't even blink. Thousands of constraints doesn't even blink either. So it's like the type of scale we're talking about is like is pretty large compared to again like machine learning problems. Like it's built for that. So like you get a lot of things out of linear programming is my point. So, so that was like a bit, hopefully give you a sense for like how does linear programming work. Now I want to talk about mixed integer linear programming. And so your question may be why? And the answer to the question is like sometimes it's not a float. So what I didn't tell you about linear programming is like there is one assumption is like every variable in your problem should be a float or a continuous variable. Like it has to be like a float essentially. And so the problem is like it's great, it's not always great. For instance, like if I go to my grocery and I tell them I want to buy 2.37 avocados, they are not going to be very pleased with me. Like what I want is I want to buy 2 or 3 avocados, right? It's not a float. There are other obvious cases, like if you want to take a decision, like should I buy the car or not buy the car? The answer 0.6 doesn't quite work. It's like I don't take 0.6 a decision. It's either true or false. So it's very useful. It would be nice if we could actually support something like integers. Linear programming out of the box doesn't. Mixed integer linear programming does. So what it does is a mixed integer linear program is a program which is going to be linear constraints, linear objective, but like some of the variables can be integers. And so what do you need to know about this? Overall, the algorithm under the hood is different. It's actually using linear programming, but like doing more stuff because it's a bit more complicated. From a coding standpoint, if you want to solve a mixed integer linear program, it's like the code is going to look almost the same. Like practically, there is no difference. You just need to know that the algorithm is different. You get the same guarantees on the solution. If you run a MILP, it will give you the optimum, the global optimum for your, so you get all the good properties of the linear programming solver. The one drawback, which is not surprising, it's a harder problem, it's slower, but you still get like very powerful results out of it. So so let's see, what I wanted to do was to show you a bit how it looks in code in F#, like if you wanted to set up a linear problem. So I'm going to use here F# and Google OR tools. So there's actually a really nice F# library called Flips, which Matthew Cruz over there has authored. So here I'm showing you like the rawest, simplest possible way you would set up a linear programming project, but Flips would help you potentially make it nicer or easier. So in this case, I'm going to open the library. It's a linear problem, so I'm going to open the linear solver. Step one is like we're going to create a solver. Like what is it that you want to solve? So if you want to solve a mixed integer linear program, you have to look at the docs and it will tell you that the SCIP solver is what you want. So you create a solver. And then the two steps I described was like first, you want to create variables, and then you want to create an objective or constraints by setting coefficients. So the variables, it's pretty simple. Here I'm creating like 3 types of variables. The typical one is like make numVar is going to create a float, essentially like a continuous variable. So here I'm creating a variable in my solver called var1. And I'm telling it also that this variable should be between 0 and plus infinity. So you can even put like some constraints on the variable as well. Like I'm saying, like I don't want to buy negative avocados. That's not possible, for instance, that type of thing. Now, if we want to do mixed integer, we want to do integers as well. The only difference is like when you create your variable, you're going to say not numVar, but like intVar. So I'm just telling the solver it's a variable, and this variable is an integer. That's the only thing which is allowed. So here I'm saying like var2 will be an integer, can be any number between 0 and 10, but has to be an integer. And the third case, which is useful to know, is an integer, a special case of an integer would be Booleans. So you can also create a Boolean variable. Here you don't really need to tell it like what's the minimum and the maximum value because there are really 2 values. So you're going to just tell it like this is a Boolean and you're done. So this is how it looks to set up the variables. Now, if you want to set up a constraint, which is going to be similar, like the objective is going to look more or less the same. So a constraint, again, is going to be a linear combination. So it's going to be something like variable times the number, plus variable times the number, and so on and so forth, is less than a certain number. If I want to set it up, the way I would do it is like I'm going to say solver, create a constraint, which I'm going to call constraint 1. Constraint, I'm going to give it like a lower bound. So that constraint, you always need to be greater than 0. You always need to be less than 100. And here I'm going to set the coefficient. So the number 1, I want 1 times var1. This is going to be set the coefficient for variable 1 as 1. This is literally like all it takes to set a problem. So like create the variables and then create the constraints and set the coefficients to the variables. Good. I wanted to talk about mixed integer linear programming because this is opening up a world of possibilities compared to linear programming. So if you represent Booleans as integers with 0 or 1 value, you could, for instance, represent something like a logical gate, like an AND gate. This is interesting. So suppose you have a variable A, which is a Boolean, B, which is a Boolean, and what I want is like I want to create a variable X, which is A and B. In a language like F# or in most languages, you would say this is trivial. Take A, multiply by B. This is doing AND. The problem with linear programming is that you cannot do that because like, I cannot multiply A by B because this would create an equation which is not a linear equation anymore. So I'm not allowed to multiply them together. But with a bit of trickery, I can create an AND gate. So this is going to take a bit of fiddling. Is like I'm going to say X has to be between 0 and 1 because it's a Boolean. X needs to be less than B, which is true. And that way, like if B is 0, X is going to be 0. So that's like one part of the AND gate. If X less than A, so if A is 0, X is going to be 0. And the last part is like X is going to be greater than A plus B minus 1. And this is going to enforce that when A and B are 1, X is going to be 1. So we replicated an AND gate here. It's not pretty, but it's interesting because I think as a software engineer, if you realize that you can replicate AND, OR, NOT, XOR, IF, it opens like a ton of possibilities. So you can do a lot with mixed integer linear programming. So going to finish up, or like to start to move to kind of my conclusion on like applications and limitations. So as a software engineer, you probably have heard the expression, like if your only tool is a hammer, everything looks like a nail. And usually that's not meant as a compliment, like it means like you're really trying to use the same tool everywhere because that's the only thing you know, and you're trying to use it even in cases where maybe you shouldn't. The reason I'm bringing up that expression is because what if the hammer in question was a very big hammer? And the point, so the reason I'm bringing that up is because like in the previous slide, what I showed you is like an absolutely horrific way to represent an AND gate. Like, it's an AND gate, it takes like 4 constraints, it's pretty tricky. And so it's like you could tell me here, it's like, okay, that's great, but like why would I go to all this pain to create an AND gate where I can just like use any normal programming language and I'm done with it? And for me, like the big value you get is like it's a bit costly, but you get a massive hammer with linear programming. So why is it a huge hammer? Because like the alternative is like if I want to optimize a function without linear programming, I'm probably going to use something based on gradient descent again. And like if I do that, is like there is a lot of things I'm not going to get. For instance, like I'm not going to get a guaranteed global optimum. Typically when you do machine learning, you write your code and then you're going to run it for like 1 hour, 1 day, 1 week. You hope it converges. You hope it found the maximum. You don't know. Like linear programming, if you can write it as a linear program, you know the solution is the right one and you're done, like, which is awesome. Plus is like it consumes less energy, like no fiddling. The other one is, like I mentioned, that constraint handling is that you're going to get a solution which is respecting constraints, which is something which is not trivial to do with like traditional gradient-based methods. And the solvers are, again, like very efficient. I mean, it's like that's the benefit of using something which dates back to the 40s. People had like almost 80 years or 90 years to improve on the algorithm. So like they are like tuned to death. So, and more broadly, like if I had to summarize what I'm saying here, is like if you see a problem and you see that it's a linear programming problem or a mixed integer linear programming problem, you are done. There is like no tuning of your model. There is like none of that nonsense. If you can write it as an LP, you're finished. You just write the LP, you pass it to the solver, and you just go back and relax and have a beer or like whatever you want to do on the weekend. Like it's pretty awesome. Applications. So where is this useful? Like first, like many problems are linear. Probably if you work in a company which is producing things, you probably need linear programming more than machine learning. Like any problem, like creating a schedule, deciding like where to produce things, deciding how big a factory should be, these are born for linear programming. If you have things like a network, like your company is building things and also shipping things, networks born for like linear programming. Like you can do a lot of it, like to optimize network flows. So in particular in like supply chain, in manufacturing, is like it's like a godsend. Like this is what it's built for. Another way to say this is like if in your problem you see things like I would like to see how to get the lowest total cost. Total cost is a linear function. It's going to be price of something times how much plus price of something times how much. Chances are you can write it as a linear program. Total weight, same thing, total volume. So that type of thing, like it's absolutely everywhere. With some tricks, I mentioned that mixed integer linear programming can do like a lot. Like actually, I've been doing a lot of linear programming over the past 2 or 3 years. And I didn't realize like how much you could do with it, or like it's like every day I discover that I can do actually more things that I didn't think were possible. So it's like you can do a lot with it. I was actually thinking during Harry's talk too, where he was talking about resilience of networks. I was talking about Matthew a bit earlier. I was thinking like if your question, for instance, like here is a network, what's the most efficient way to essentially mess up the entire network? You can probably, this is probably a good case for using linear programming. Like, how could I reduce the flow in the network for the lowest cost would be a very good fit for this. So it's like, there is a talk maybe in the making for like how to use linear programming to be an evil villain and destroy the world efficiently. But, and sometimes your problem is not linear, but like that's going, if you are, how to put it, like if you're tolerant enough, like anything can be linear or approximated by a straight line. Like if you're tolerant enough, like a straight line represents a lot of things. It might not be correct. I mean, the point here is like every model is wrong. Some of them are useful. So sometimes it's like you might get away with making a problem linear, even if it isn't, because like then you can use the hammer. And the other piece where like is worth thinking about is like sometimes your problem is not linear, but some subparts of your model are. Like maybe you have like a big optimization model, and in the middle there is a piece which is about optimizing transportation. You could actually solve the subproblem using linear programming and solve the bigger problem using something else. So another way you can use linear programming. Limitation. A lot of times, like if you're tolerant enough, you can make it linear. Sometimes you can't. Not everything is linear. Maybe, like for instance, also like Matthew again, like pointed at the fact that I might be wrong, but if you see something like least square optimization, least square linear regression, chances are it's not going to work with linear programming because what you're minimizing is a function which is doing squares, which is not linear. So sometimes it will not fit. Like sometimes like the hammer will, even the hammer will not work. And like maybe it's, I don't know if it's really fair to say it's a limitation, but like unsurprisingly, the bigger, first like mixed integer linear programs are going to be slower than linear programming. And like it's going to handle like massive problems, but like there is a limit too. Like at some point it's going to get slow. It will always work, but like it cannot handle everything. That's what I had. So I hope it gave you a bit of a sense for like what linear programming is about. Really what the takeaway for me is like, I suspect like some of you have never heard about linear programming before. Some of you might have heard of it but forgotten about it. I really think it's like an incredibly underrated tool, and like every person who's interested in optimization, in like modeling, like should know about that tool because you can do an amazing amount of things with it. Tomorrow, I'm going to do a 3-hour workshop which is going to be hands-on, 4 levels of linear programming, going from the simplest problem you could do to probably the hardest problem you could do. If you want to know more about it and see how it looks in practice, is like come to the workshop. And that's what I had for you. So thank you for listening to me. And if you want to find me online and stuff, like this is me here. Thank you.